Hello, my name is Ivan Maksimov and I'm going to present to you my work on hierarchical graph embeddings for addressing cold start in recommender systems. Well, generally, cold start for items is a problem when new items are introduced, there are few interactions with them, thus item embeddings are not stable, and this leads to poor performance of recommender systems. However, recommending new items is crucial for many businesses like fashion, films, video games, and many other. But current algorithms do not support well cold start out of the box. So we introduce some kind of hierarchical tree-life graphs to address cold start problem for items. Thus, incorporating these item-item interactions, we try to avoid cold start for items. So generally, we introduce new graph-based method which is especially designed for recommender systems and uses so-called vertical convolutions on tree-like graphs. It is fast and yields superior performance in terms of metrics. So what is hierarchical graph embedding model? Well, main idea is to use item hierarchy graph. Generally, we have items. Suppose we have some particular yogurt brand. Of course, it has some high-level category yogurts. Yogurts have more high-level category milk products, and so on and so forth. So we want to use this item hierarchy graph. So each connections are presented with a separate hierarchical graph embedding layer. So what is hierarchical graph embedding layer? Well, generally, first of all, we get item embeddings in a usual way with an n-dot embedding. Then we have this formula. So generally, graph embedding layer consists of graph adjacency matrix multiplied by two learnable parameter matrices with ReLU, and then we apply softmax and residual connection. So this architecture is pretty simple, however, it is very fast, yields superior performance, and is very robust. And we will show later why. We tried 5 datasets from movie lens to retail rocket. These datasets varies by interaction size from 100,000 to 12 million interactions, and also there is a different number of hierarchy levels from 1 to 4, and we are going to show that also number of hierarchy levels affects model performance. To make training and test set, we reserve last 2 weeks as a test set, and for train we sample 20% of items and then we randomly drop interactions with them to simulate cold start problem. This methodology was described in the work of Osiliadis and Frolov called hybrid SVD. To measure performance, we use hit rate at K and precision at K, and for K we use 10 and 20. As alternative models, we assume some classic ones like matrix factorization by Simon-Funk, alternating least squares, and association rules with item taxonomy. We also compare our model with modern hybrid matrix factorization and LightFM, which are hybrid models and can also incorporate side information on items. Moreover, we compare our model with graph convolution matrix completion, which is a graph-based model. So as for results, you can see that for Retail Rocket, Amazon, and X5 Retail Hero, hierarchical graph embedding model outperforms all other models. However, for MovieLens 1M and MovieLens 100,000, it is pretty robust and is at the same level as top alternative models. Why? Well, first of all, Rivera-Castro, Amazon, and X5 are pretty big datasets. Moreover, they have 3 or 4 item hierarchy level. However, MovieLens has only 1 item hierarchy levels. So our model really works well only when multiple hierarchy levels are presented. However, it is pretty robust even for small datasets with only 1 item hierarchy level. So why this method works? Generally, hierarchical graph embedding models yields more clustered embeddings. For example, as for matrix factorization, you can see that the biggest category, grocery, forms only 1 cluster. However, in reality, grocery has some subclusters of smaller categories, and hierarchical graph embeddings really yields clustered grocery category. We also did a ablation study on hierarchical graph embedding model in terms of precision at 20. We tried to remove skip connection, but it yielded to 17% decrease in precision at 20. We also tried to add attention, however, it improved the model, but also increased computational complexity. So we decided not to include attention in final architecture. Also, we replaced weighting matrix W with learnable parameters W1 and W2. W1 and W2 is matrix factorization of W, and it yielded to faster training, faster predicting, and moreover plus 1% of precision at 20. We also tried some other ablation studies. Which is also important is that increasing hierarchy levels from 1 to 2 and from 2 to 3 really results in model performance increase. So our model works really much better when there are multiple hierarchy levels. Also, this method has some drawbacks. First of all, it needs pretty big batch size of more than 2000 items per batch. This big batch size increases computational time a bit, and also it needs special stratified sampling technique if there are many categories. Also, we discovered that the method needs many items per category. Indeed, it works better than baselines if there are 150 or more items per category. So generally, when you should use hierarchical graph embedding model? Well, when there is a cold start problem on medium and large datasets, which has many category levels, and when there are more than 50 items per category. More generally, when the user item matrix is sparse, but item hierarchy graph is not. So finally, we created fast and scalable graph-based method for hierarchical tree-like graphs, which yields superior performance in cold start for medium and big datasets with rich hierarchical information. It is pretty robust and just a bit slower than vanilla matrix factorization. Thank you for your attention.